Hey everybody, welcome back to 3 Deviations. We're really getting down to the wire here. Last 3 videos of 3 Deviations for single order calculus. We're getting started. Today we want to talk about polar curves and derivatives of these polar curves. So this follows kind of similarly to how we discussed the derivatives of the parametric equations, which of course was a fairly easy task. This is a little bit more nuanced. It's a lot harder than just dy dx, right? Or dy dx equals dy dt over dx dt. We have a little bit more nuance with these polar equations, but it really turns into something quite beautiful. Anyways, we're going to get started, and we'll discuss how we take derivatives of these little friends. All right, here's a definition for you. We're going to talk about the derivative, and we're going to derive the derivative for these polar curves. So we know that we have our relationships to convert between polar and rectangular coordinate system such that x equals r cosine theta and y equals r sine theta. Okay, so we need to determine how we take a derivative. So we want to find dy over dx. Now, this is a very strange task. You want to find dx, where we are actually trying to find x or y prime of theta over x prime of theta. Now, as we discussed with parametric, this is quite easy. However, now we need to reference these friends here because these are going to make things a little bit more complicated. So r is our actual function. So the way we can actually write this is x equals r of theta cosine of theta, and y equals r of theta sine of theta. Now, what does this mean? Well, this means that we actually have two functions of theta defining our x and y values. So what we need to do is we need to employ some more, or some less elementary differentiation techniques in order to find what our actual tangent slope is going to be. So how do we do this? Well, what we're going to do is we're going to employ the product rule to get y prime over x prime. So y prime, we can take the derivative of this friend here. We need to use the product rule. So we take dr d theta, which is the derivative of the first term times the second term sine of theta, plus the second term, or plus the first term r times the second term, times the derivative of the second term cosine of theta. Derivative of sine is cosine, as we know. And we do the same for x prime, and we get x prime is equal to dr d theta cosine theta minus r sine theta. Okay, now this is actually a very important set of equations that we have for converting between polar and rectangular form for the derivatives. It's a very important formula that you will be looking at later on when you get into Jacobians, but that's for a later date. Anyways, we have these expressions. Now we only need to divide by them. And I'm going to adopt a new nomenclature that I discussed in my parametric equations video anyways, but basically I set, if anything is with respect to theta, then that's r dot, or dr d theta is equal to r dot, because theta is our big independent variable, whereas in parametric t was our dependent variable, or independent variable. So now if I'm differentiating with respect to theta, I'm going to use r dot. Okay, so we get dy dx is equal to r dot sine theta plus r cosine theta over r dot cosine theta minus r sine theta. Okay, now this is a very complicated formula, but you can always derive it. You can always derive it from this and just take the derivative and you find dy dx. Now, this isn't something you need to memorize exactly for that reason, because you can just rederive it however many times you want. Anyways, let's try an example. Let's try to find the tangent line for the polar curve r equals 1 plus sine of theta at theta equals pi over 3. Okay, so we need to determine two things. We need to determine what our function is and what our derivative is. Luckily, our function is defined right there, and our derivative we just need to fetch by doing some very simple techniques. So dr d theta equals r dot is equal to cosine of theta. This one cancels out, and the sine goes to cosine. All right, now we have a line of trigonometry that really makes me cringe a little bit just looking at it. But anyways, this is just an application of our formula that we determined in the last slide. So we get dy dx obviously equal to r dot sine theta r cosine theta over r dot cosine theta minus r sine theta. now we just substitute in our new r dot. So we get cosine theta plus 1 plus sine theta cosine theta cosine theta minus 1 plus sine theta. Okay, now we can evaluate this. We can rejigger it. We can rejigger this however we want to best suit our needs. We can use whatever trigonometric identities we need, but that's in the past, so we don't need to reevaluate those. Anyways, moving on, we get cosine theta times 1 plus 2 sine theta over 1 minus sine theta minus 2 sine squared theta. We can factor at the bottom, which gives us cosine theta times 1 plus 2 sine theta over 1 plus sine theta 1 minus 2 sine theta. All right, so now we are prepared to evaluate this at pi over 3. So we get dy dx at pi over 3 is equal to all of these evaluations that we have. So we get 1/2 1 plus root 3 over 1 plus root 3 over 2 minus 1, or times 1 minus root 3. We get 1 plus root 3 over negative 1 minus root 3. Obviously, 1 is the negative of the other, so we get negative 1 as our slope at pi over 3. So what this means, basically, is that at our function, we will have pi over 3, so we will have some magnitude that goes to pi over 3. So we can actually determine this magnitude. So r of pi over 3 is equal to 1 plus sine of pi over 3, which is equal to 1 plus root 3 over 2, because sine of pi over 3 is root 3 over 2. So what we know is that at pi over 3, which is about this angle, we are 1 plus root 3 over 2 units away as our magnitude. Now at this point, we're going to have a slope of negative 1. So we're going to have a slope that looks like this. So we can kind of determine what it looks like. It turns out that this graph is what we call, I believe it's called a limaçon. It's a French word, limaçon. And it looks a bit like an upside-down heart, or maybe something's best left unspoken when they look dimpled like this. But anyways, we get something that looks like this, and it has a tangent line of negative 1 at this pi over 3 value, at theta equals pi over 3. All right, so that is the derivatives of polar curves. As you can see, you can apply this formula pretty much everywhere that we have in units 2 and 3, but just to polar equations. So I don't think there's a big need to keep redoing all this derivative stuff, just because it's just a reapplication of this formula. Anyways, in the next videos, though, for our last topics, integrals of these polar curves is quite a lot more nuanced than most people imagine, and it's something that we'd want to cover more in depth. Now, as I said earlier, this unit is mainly a bridge unit between multivariable and single variable calculus, and taking integrals of these polar curves and learning about integrals of parametric equations, how they relate especially to vectors, which we'll discuss in later units. Something that's extremely important for how we view our multivariable world. Anyways, thank you for watching, and we will see you in the next video, second to last video, I believe, for single variable calculus. We'll see you then.